All right, thank you, Catherine, for our last 6-minute talk. Logan Scully.
It changes density. It creates convection.
So it's going to have, because there's water around it, it's going to rise.
And I will come around that goes to that. That goes to that. Now that's assuming again, if you think about it, the way the setup is set up, once the thing is heated up, right, the water stream is coming out. I'm assuming water should be going back in. Otherwise, the thing is going to build on itself.
Make a vacuum almost.
Yeah, exactly. And then you got a bigger problem. You're going to hot spots, right? At certain locations, you don't mean steam. Unless it's really, really hot, right? And then it will blow up on your head. See, if I was running that gun, I would make sure it never gets to steam. I would make sure it's full water.
It almost seems like you have some kind of pump though.
Yeah, I don't think
Circulate water instead
Yeah,
of.
they're probably going to pump. So I would do it in 10 minutes. That's whatever. I mean, 5 minutes. Another 8. Yes.
Good afternoon, everyone. My name is Logan Scully, as you know, and for my 6-minute talk topic, I chose the Yeti Rambler. Coincidentally, Austin also chose the Yeti product.
And I approved it. I thought it was going to come back to. I have another section tomorrow.
So a lot of my information is going to be very similar. I just calculated my example in a different manner.
Yeah, much simpler.
So, just a brief outline of what I'm going to cover. I'll cover the history of a thermos, and a Yeti is just a updated or re-engineered version of a thermos. I'll cover the components of it, the relationship to thermodynamics and heat transfer, give an example, and then I'll have a brief conclusion. So the history of a thermos, or a Dewar flask, is that it was created in 1892 by James Dewar, and it is, the way it's constructed, it's 2 cylinders, one inside the other. They are connected at the neck only. Normally there's either a space here, so where there's vacuum where it is, or there is a material that has low conduction. And in the thermos, the gap between the 2 materials is actually at vacuum. So as we know, the 3 modes of heat transfer are conduction, convection, and radiation. And in our case with the thermos, or in the case of the Yeti, we only have loss or heat transfer due to radiation. And this is because in the case of a thermos, we have a silver lining or a silver coating, which only allows a radiation in one direction, compared to if that silver lining or coating wasn't there, we would have it in both directions. And since it's at vacuum, we do not have conduction or convection, or it's very low. The Yeti Ramblers came out in around 2014, and Yeti, they use a copper coating instead of what was previously been used a lot as a silver coating. And the copper coating has a lower emissivity than the silver coating. So the theoretical background, or the relation to thermodynamics and heat transfer, are the energy conservation. For the case that I'm going to cover, we only have heat transfer due to conduction, convection, and radiation. But in our case, we only have it due to radiation, not convection and conduction, because of the vacuum. And the equation used is the rate equation for radiation. So as I said, our total heat transfer is going to be through radiation, and for this scenario that I'll cover in a second, I chose, or the specific case for the rate equation of radiation was concentric cylinders, because we have one cylinder inside of the other in vacuum. So we have the Boltzmann constant, the area of the surface, the difference in temperatures, and the 2 different emissivities that are going to play a role in the calculation. So in the case that I have here, I just want to show that the way that a Yeti works is because of the lower emissivity value of copper to the emissivity value of the silver coating. So in this case, we have a Yeti cup or a Yeti Rambler and a thermos. They are both the same diameters. They are both filled with coffee, and where the coffee is at the same temperature and the surroundings are at the same temperature. For the thermos, the silver coating, I use a emissivity of 0.052, and for the Rambler, it has a copper coating or polished copper, which has a value of 0.035. So we use the Boltzmann constant and we multiply it by the area and the temperature difference. So for the thermos, we have the emissivity of 0.052, and in the thermos case, we have a heat loss through the coffee of 0.61 watts. And for the case of the Rambler, we have the heat loss through the coffee of 0.40 watts. So in conclusion, to prove my point again, the Yeti Ramblers work better than the thermoses because they use a copper coating instead of silver, which has a lower emissivity than the thermos, which is the silver coating. In our case, the Yetis or thermoses in general, they're created to either keep drinks hotter for longer periods of time or keep them cooler on a hotter day. Are there any questions?
Okay.
So we haven't covered this in heat transfer, and I realized that once I chose the topic and started going through the process. My initial process or my initial equation was what Austin did, and I kid you not, I sat there for probably 3-4 hours, not even realizing the time, trying to figure out what was going on, and I realized that we hadn't really covered that material, and I found this equation and read up on it in chapter 13, which I don't even think we're gonna.
No, you get it.
Oh, so we do get to it?
Yeah,
So
I do.
I scratched my head for the longest time.
But you could have simplified this, if you, I just did the math.
Okay.
You could have, there are two questions now. Let's keep transfer problem. You didn't even have to worry about constant cylinders. If you just set epsilon 1 for the silver one, case 1, epsilon 1, epsilon 2, whatever, epsilon copper, epsilon silver,
Yes.
your numbers will barely change.
Okay.
Because your R1, R2 values are so close,
Yes.
right? And you're sitting at 0.61, I think,
Yeah.
0.41. You still make the same conclusion that you're getting 33% less heat loss, right now, heat not leaving the system.
I chose that example, I just wanted to show
Yeah,
that.
that's perfectly fine. So that's one. You didn't have to worry about the 1 or epsilon. You
Okay.
could have just simplified even further. But this is probably a little bit better. This becomes an issue when damage is alive, right?
Yeah.
All of us. Next question. Let's assume you guys want to start your own ATs, right? You want to call it Tiger tumbler or something. What do you do? There's a clue in there. There's
What
a
do you
clue.
mean by, what do you do?
Let's say you want to start your own business.
Yes.
You want to.
Well, I'm just gonna take,
No, you don't need to. Radiation is very surface effect. Copper costs lots of money. You
Yeah.
go broke trying to sell that thing.
Cover plate the whole thing.
No, you don't have, maybe. Why copper? See, remember the advantage was silver became copper, epsilon went from 0.035 to 0.05 to 0.035.
Yeah.
That 30% difference is what you're saving. Essentially, it's 1:1 correlation, correct? So next step is to go find a metal or create a new surface that has 0.02,
yeah.
right, or 0.01.
There are surfaces, and I was thinking about that, but I was also wondering, like, so why wasn't this done previous to Yeti, was like my question I was asking myself. Like, why in 2014, when he created this in 1892, why now all of a sudden did they choose this? And my only conclusion that I could come up with was the cost of it. So maybe over time, the cost of the copper went down, and they also had some new process that it was cheaper to manufacture.
They probably
Because there are, the values where I got my polished silver and polished copper, there's hundreds and hundreds of materials that could be used that's polished or annealed or like just different processes. They all have different emissivities, and there were some that were way lower than copper. So my only conclusion that I came up with it would be that it was the price of manufacturing it, or the way to get it.
Silver must be used to electroplate. It's very used to electroplate silver.
Yeah.
Copper must be hard, I'm assuming. I'm not electroplate.
Yeah, I couldn't.
They probably figured that out, how to electroplate copper.
It must have been a breakthrough on on price is why they were able to use copper.
They will charge you more, don't they, from what I hear? It's not a bit more expensive. No.
Oh, Yetis are, you're talking about the price of the Yeti? Oh, yeah, I mean, the cup that she has is actually a Yeti. So once Yeti came out,
Well,
companies took their design, they cut it open. You have the Ozark one.
I have a cheap, like.
Yeah, I know, but it's literally the exact same thing. I watched a video where they cut them all open. There's no difference. The only difference is a tiny difference in millimeter thickness of the material. So once Yeti had it, other people just cut it apart and wanted the same efficiencies, so they just changed their thicknesses, and that's how they got away with basically stealing their design without actually taking their exact design.
So is it the same technology in ice chest too, or is that?
So that has something to do with insulation. It is very similar, but I think it's not vacuum because it's
Which one? Material.
okay. So Yeti makes the cups, the ramblers and tumblers. They also have their ice chest.
Ice chest, yeah.
So it's similar concept, but instead of vacuum, they have a insulation material for insulation.
Yeah, that was, the vacuum was dangerous there.
Yeah.
Strength
So
of the
that's
material.
why. But originally, from what I found, the original Dewar flask was glass and it was silver lined. And they moved away from that, obviously, because it's a lot easier to break.
Is it a complete vacuum inside the cup, or is there?
So it's
some-
partial vacuum. It's as close as you could possibly get without actually having like
It costs a lot of money to create actual vacuum.
yeah. So like on the Yeti cup, the reason you have yours,
Yeah.
does yours have a cap on the bottom? Yeah. So the cap at the bottom is because they suck the vacuum, they create the vacuum from the bottom. So there's a hole, they suck the vacuum and then they tap it or weld it to create that partial vacuum between the two materials. And a lot of the materials, or the cups, they use copper plating on one side. I just chose to try to simplify it more using both walls having it, because I just wanted to show that the copper versus the silver, the difference was that the loss was lower.
That's what makes radiation so hard, because if you change the other material, leave one surface same and change the other one, you get completely different.
Yeah, it's completely different.
Yeah, and that's what makes it screws the whole thing up.
So just for the simplicity of the calculation and just to get my point across, I just chose for both walls to be copper. Where in the cup, it's actually, I don't remember if it's the inner or outer wall, but only one has the copper coating on it.
It's the very inner.
So it's the inner closest to the liquid?
Yeah.
Okay.
Okay, so I'll see you not next week.